Savannah, because I teach 4 Physics 11s, I teach the same lesson 4 times, and my brain is twigging right now. I may have forgotten to say something with you. I can't remember. So if I'm repeating myself, I apologize. But here's what we want to really emphasize from last day. First of all, we were looking at types of forces. We talked about the force of gravity. We said that that was mg. What's another word for the force of gravity? Okay, you need to know that. The fact that there was stunning silence here concerns me. I will say to you, an object has a weight of blah, blah, blah. What I've just given you is mg, not m. Okay, that's important. What are the units for mass in the SI system? What's mass measured in? Did I tell you what the imperial unit for mass is? So the imperial unit for force is pounds. The imperial unit for mass, it's slugs. I think I may have told you that I was going to tell you and I forgot. What a stupid unit, by the way, but slugs. So we talked about mg, and then we spent a lot of time talking about the normal force. What's the normal force? That's how hard the ground or the chair that you're sitting on or the table, any surface has to push up against an object to keep that object from sinking into it. And we know it must be there, Logan, because of Newton's laws. We were able to reason that it was there. But up until yesterday, last day, up until then, we called it F ground or F ice or F table or F wall. That's all the normal force, the force from a surface. I don't have a formula for the normal force. You're going to do a good free body diagram and figure it out. There is no equation for normal force on your formula sheet. We said that if you do a free body diagram, really we're saying if you're not sinking into the ground like quicksand, you're not flying to like Superman, everything down has to equal everything up, or everything up has to equal everything down. That's your equation. Good free body diagram, and then get the normal force by itself. And then, here was the key idea as well. Courtney, what does a scale measure? Does a scale measure mass? Does a scale measure weight? What does a scale measure? It measures the normal force. In fact, I said to you, a good amusement park ride, all it does is it mucks around with the normal force. Now, lesson 2, this is lesson 3. Lesson 2, which was free body diagrams, there were a couple of questions there that were pretty nasty, specifically number 3 and number 9. I'm going to say to you in a couple of days, maybe next class, I think, I'll go over those questions, but I want to let you wrestle with them first. If from lesson 2 you're having trouble with number 1 or number 2, yeah, you want to hit me up during a flex block or after school and I can help you. But if you're finding number 3 and number 9 tricky, you're, no pun intended, normal. Not in the force sense, but in the average sense. Okay? All of you, when you feel gravity acting on you, you're not actually feeling gravity. What you're feeling is the normal force pushing back up through you. When I jumped out of an airplane, I mentioned I jumped out of an airplane. When I jumped out of an airplane, what was the normal force on me? Was the ground pushing up on me at all, Ben, when I jumped out of an airplane? So as a number exactly, what was the normal force on me? I felt weightless. Was I weightless? Well, that would mean that there was no gravity. Was there still very definitely gravity when I jumped out of an airplane? Okay. If you don't feel a normal force, you'll feel weightless. In fact, we often say that that's apparent weightlessness. True weightlessness, by the way, is when you're in the middle of outer space and there's no planets around and there's no gravity acting on you. What holds the moon in place around the Earth? Which force? Begins the letter G. Gravity. So does gravity reach all the way out to the moon? Say yes. So does gravity reach all the way out to the International Space Station, which is way, way closer than the moon? So why are the astronauts floating? It's not because there's no gravity. It's because there's no normal force. You see the difference? So now, pick up your pencils, here we go. This is why astronauts in the International Space Station float. It isn't that there's no gravity. Gravity reaches all the way out to the moon and further. It's that there's no Normal force. Remember, another name for gravity is weight. And another name for the normal force, Rowan, is your apparent weight. What you think you weigh is the normal force. That's why, by the way, Rowan, when you're giving somebody a piggyback, you feel heavier. What's changed? How hard the ground is pushing up through your feet. You didn't gain mass. Gravity didn't change for you. It's just something else is pushing down on you. The ground has to push up harder, and your legs are going, wow, I'm feeling the ground pushing up harder than I used to. I must feel heavier. Your apparent weight has changed. With me on the argument? So, on the International Space Station, the apparent weight, the normal force, is equal to exactly what? As a number exactly, Ben? Why? Hint. See part F above, or Ben, remember the question that I asked you about 5 minutes ago that you also gave me 0 as an answer. Why? What? Say it loud and proud. What?
They are.
The International Space Station is not floating up there, it's falling. They're in free fall. They're in free fall. So the real question isn't why they don't feel a normal force. The real question is, why isn't the International Space Station crashing into the Earth? See the difference in questions there? If you're in free fall, Logan, you won't feel a normal force. Oh, and because they're in an enclosed room, they don't feel the breeze on their face that I felt when I jumped out of an airplane. I mentioned I jumped out of an airplane that I felt, which told me I was falling. They don't have that. Put your pencils down and look up. I'm going to draw a picture. It's going to suck. Earth. I'd like you to imagine that we had a big mountain on the Earth with a cannon. And we fired a cannonball. Boom. It would land there. What if we put more gunpowder in it? Boom. It would land there. What if we put more gunpowder in it? Boom. It would land maybe right there. Could we put just the right gunpowder so that when we fired it, even though it was always falling, it never got any closer? That's what an orbit is, and that's what all of our satellites are doing. All of our satellites are falling, but we give them just the right sideways speed. You'll learn how to do it in Physics 12 if you take Physics 12, so that they never get any closer to the Earth, even though they're always falling. And that's why they are apparently weightless. Are they weightless? No, gravity's acting on them, very much so. But if you're in free fall, you feel no normal force. I think, and in fact, I think it might have been Antonio, sometime before Christmas, I think during a lesson you and I were having a conversation, and I think I promised that I would explain to you why it is that the astronauts in the International Space Station are floating. It's not because there's no gravity, because they're falling to the Earth, and as long as we give them just the right sideways speed, they'll never hit the Earth. Is that okay? Oh, why couldn't you do this on the Earth's surface? Air resistance would slow you down so much, but in outer space, no air, you'll just keep going in a straight line. Sorry, at a steady speed, not on a straight line, because there's a force acting on you, but at a steady speed, you won't slow down. Is that all right? Put your pencils down, look up. Answering your question now, Riley. Example 2, I think, matches the last question from the homework. I didn't do an example like this. So it says this. Person is standing on a bathroom scale while inside an elevator. I think we're talking about a normal force. Okay. What is the magnitude and direction of the elevator's acceleration if the scale reads 32 kilograms, 64 kilograms? Okay. You know what this is a good job for? There's a punchline there, folks. You know what this is a good job for? Courtney, a free body diagram. Darn right. Riley, we're going to do a free body diagram. Here's the person. What are the forces acting on him? Get the obvious one. Which way? What else? Well, they're standing on a scale. The ground is pushing up. What do we call that force, Riley? Bigger, smaller, or the same size as mg? Now, in some of the questions, I told you which way we were accelerating, and it was obvious. Here we're going to have to do some thinking. What's this person's mass? What's the scale saying their mass is? Are they feeling heavier or lighter? Which way are we accelerating if you feel lighter? So which way am I going to draw a smaller arrow? So that's step one. I can figure out, that's an N, by the way. I can figure out that the normal force is smaller because they feel lighter. You okay with that? Who's winning? Yeah. Who's losing? Yep. What's that always equal? MA. What am I trying to find here? I got MA. What am I trying to find here? Find the magnitude and direction of the elevators. Oh, how do they get the A by itself? Yeah, I love the way you did that. You looked at me. Well, divide M. Yes. So can you do me a favor, Riley? Let's go. Boom. There's my equation. Do I know M? Say yes. 45. Do I know G? 9.8. Do I know the normal force? I don't. You might say, Mr. Dueck, isn't that the normal force? Isn't that kilograms? So, you ready? To change a mass, kilograms, into a force in newtons, we multiply by 9.8. That's the conversion factor. That's really what your bathroom scale is doing when it gives you your mass in kilograms. It's dividing the normal force by 9.8. That's all it's doing. So to reverse it. So, ready? Riley, what was M? G, 9.8, minus the normal force is going to be 32 times 9.8, divided by the actual mass. What's the magnitude of the acceleration? What do you get? Oh, is this a fraction, Courtney? More than one thing on the top? Brackets around the top. Do I need brackets around the bottom? No. 45 times 9.8 minus 32 times 9.8 divided by 45. 2.831, 2.83. I'll go to 3 sig figs. Meters per second squared. Direction. Which way did you say we're accelerating, Riley? Yeah. Is that okay? Do I need to do B or are you okay? By the way, B, are we feeling heavier or lighter? Which way are we accelerating? Who's winning? Elevator didn't show up anywhere in here. Ah, I think in B it's going to be normal force minus mg equals ma. Divide by m to get the A by itself. I don't know the normal force. It's the scale in kilograms times 9.8. That's just how scales work. That's not a physics trick. That's just, I know that's how scales work. Do I need to do B or you? Would that get you through number 2? Okay? Okay. I did promise I would go over the answers to section A. If you haven't done this yet, don't just circle the answers and think you're learning. Okay? So circle the correct answers. It says this: comparing the concepts of mass and weight, one is basic and fundamental. Which is the basic and fundamental one? Mass. Which one depends on location? No, now. Wait. Let's change colors so it's easier to see when I print this. What is the measure of the amount of matter in an object and only depends on the number and kind of atoms that compose it? That's mass. Mass is a measure of the laziness, although I think I used the word stubbornness, inertia, stubbornness. The more mass you have, the harder it is to change your acceleration, the bigger force we need to apply. That's really F equals ma. Which one is related to the gravitational force? No, now. Which one depends on an object's location? No, now. Mass does not. So a stone would have the same mass or weight on the surface of the moon. Yep. But its weight would be different. On the moon, where gravity is only about 1/6 the Earth's gravity, which would be the same on the Earth? Mass, weight, or both? Just mass. That's why we were able to build bulky spacesuits and the astronauts could still wear them. On the Earth, they were terribly tough to walk around in because they had so much weight. Well, mass and weight are not the same. So here's a word I'm not going to ask you, but they are directly proportional. And what that means is if your mass gets twice as big, your weight gets twice as big. If your mass gets 3 times as big, your weight gets 3 times as big. So twice the mass, twice the weight. What's the SI unit of mass? Kilogram. What's the SI unit of force? Newton. Is that okay? Alrighty. Lesson 4. Finish a lesson from, go over homework question number 1. Oh, I would have remembered. I did have it there. Silly me. The last force we're going to talk about for a while. Sorry, that's a lie. We're also going to talk about friction next class. Our next force we're going to talk about is air resistance. Now, Adam, I've talked about air resistance just a little bit already. So air resistance is the force of air molecules bumping into an object that is moving through the air. By the way, the fact that when you move your hand you can feel a force, it also tells you that air must have mass. Because F equals what? If we can apply a force, it's got a mass. Here is the key idea. The force of air resistance is always the direction opposite to motion. So if you're asking what direction is the force, which way are you moving? It's in the opposite direction. It says draw a free body diagram for each of the following. A ball being thrown, a rising ball including air resistance, and a falling ball including air resistance. Okay, so I don't have my tennis ball here. There it is. In situation A, we're talking about when my hand is doing this, but not when it's left my hand. Okay? So when my hand is doing the upwards motion to throw the ball. What are the forces acting on the ball? Get the obvious one. Sorry? What else? By the way, rather than representing the mass with a dot, I'm just going to label the picture that they gave me since they gave me a lovely picture. Technically, that's not a free body diagram because you're supposed to represent the mass with a dot, but you're going to see for the rest of the unit, if they give me a picture, I'll just label the picture because it's less work. What else? Well, as I do this, which way is the ball accelerating? So which way must there be a bigger unbalanced force pointing? So the first thing, I can use Newton's first law. I know there's a force, and I'll exaggerate it. What force? I heard someone murmur it. We could call it a normal force because it's the force that prevents the ball falling through my hand. If you called it F throw, I'd probably say, sure, I know what you're getting across. There's not really a formal name for this. So sure, let's call it the normal force. And again, I know it has to be bigger. By the way, watch. I'll show you a normal force that's less than mg. Watch. There. Did the ball move up? The ball move up? Did it accelerate up? No. So I know that in fact, that's probably equal right there. So for you to throw a ball, you have to have a bigger force up than gravity. Otherwise, it won't leave your hand. You okay with that? There's the free body diagram there. Now we're in the air on the way up. What are the forces acting on it? Get the obvious one. What else? What does it say to include? Air resistance. Which way? Which way is the ball moving? So which way is air resistance? And you can call it F air or F drag or something like that. Anything else? I think that's it once it's left my hand. Now, situation C. We're on the way down. What are the forces acting on it? Get the obvious one. What else? Which way? Up. Bigger, smaller, or the same size as mg? The answer is it depends. Let's assume that we've just turned direction and so it's smaller, but as we speed up, air resistance gets bigger and bigger and bigger. Eventually, it's going to be the same size. We call that terminal velocity. This, and I said it before, but I'll repeat myself. Again, this is why we're not going to be doing air resistance very much. It's a tough force to look at. We're going to talk about it as a concept. Once in a while, I'll give you enough numbers that you can calculate it, but I have to cook the numbers just nicely. This one is interesting. Example 2 says this. In example 1b, how the heck can the ball be moving up if all the forces acting on it are downwards? It's a good question. Or have we missed something? Sorry? Is it sitting on a surface when it's left my hand? Is it touching the ground when it's left my hand? So is there a normal force? By the way, I'm glad Jabber did that. People get normal force happy. They see it everywhere now. No. If you're not sitting on a surface, there's no normal force. Okay? Because that's the surface pushing back up. So if you're in the air, there's no normal force. Have we screwed up our diagram, or is this possible? Antonio, take a sip, and then you're going to be on. You ready? This relates to a conversation you and I had this morning. In B, what direction is the ball moving? In B, what direction is the ball moving? Can all of you point your fingers up? Every one of you, your non-writing hand, point. So which way is it moving? Is it speeding up or slowing down on the way up, folks? So which way is it accelerating? All Newton's laws do is they tell me which way it's accelerating. They don't tell me which way it's moving. Can this picture be accelerating down? Oh, heck yeah. Sure. So is this possible? Absolutely. Did I hear a phone? I thought I did. Maybe I'm imagining it. Newton's laws tell us acceleration, not direction of movement. You can be moving up and slowing down, well then you're accelerating downwards, which is what that picture shows. So we're not violating any physics laws, Antonio. That's just fine. This goes back to the conversation you and I had this morning. I think it was the mountain climber, right? If you're moving down and slowing down, you're accelerating up. In example 3 in 1C, if the ball is speeding up, write a net force equation. Somebody this morning said, Mr. Dueck, what do you mean by net force equation? Winner minus loser equals F net. Except we said F net was the same as what? Yeah, okay. Who's winning? In part C. Sorry, who's winning? More specific, please. Exactly as a force. Who's winning? mg. Who's losing? Air. What does that always equal? ma. Okay. Now, I had to tell you that we were speeding up. I'm saying we haven't hit terminal velocity yet. So let's look at the parachuter. I think I like example 4. I think I like example 4. A parachutist free falls for a time. He jumps out of an airplane. Mentioned I jumped out of an airplane. And then opens a parachute. His new upward acceleration is now 1.5 meters per second squared because he's slowing down while having a downwards velocity. So he's slowing down while traveling down. That means he's accelerating up. Is that okay, Logan? Yeah. Okay. Logan, what does part A say? Draw a What is FBD an abbreviation for, folks? Okay. This is a job for a free body. I won't always tell you to draw a free body diagram. You may have to clue in. This is a job for a free body diagram. Okay, I'm going to do that right here. I'll represent the parachutist with a dot. Logan, what are the forces acting on this parachutist? Get the obvious one. Logan, what are the forces? Thank you. What? That's not a force. What's the force that's acting on him? Whenever I say get the obvious one, which one do I mean? And with the equation for that is mg. Draw an arrow pointing down. Mg. Sam, which way are we accelerating in this question? Read the question very, very carefully, please. Which way are we accelerating in this question? I even underlined the word. Which way are we accelerating? Which way are we accelerating? Which way am I going to have a bigger force pointing? Did you say up? Hope you did. So, I'll exaggerate it. In fact, you know what? I'll really exaggerate it. Yoink. There. Now it's. What force is that? What force saved my life when I jumped out of an airplane? When I jumped out of an airplane? Good. Logan, what did part A say it wanted me to do? There it is. Is there a normal force? I'm not touching any surface. Okay. B. Rowan, what did B want me to do? Who's winning? Who's losing? Equals. There's my force equation. By the way, are you starting to see why at the very beginning of this unit I told you I cannot give you an equation that fits everything? You're going to have to derive it. A free body diagram and winner minus loser. Evan, what's C want me to find? How would I get F air by itself? Yep. Sure. Did they give me the mass? Yes. Did they give me A? Yes. You saw meters per second squared? By the way, are you learning? You look for units, not the number. It's how I do it. And they gave me the mass, G 9.8. Here we go, plug and chug. So air resistance at this moment in time is going to be 90 times 1.5 plus 90. Do I need to put in a negative 9.8? No. In fact, can you see where I took care of the negative? It's right there. So as long as you have your direction, who's winning? You don't need to put a negative in for the 9.8. You've taken care of that. How big is air resistance? 1,017 units? Because it's a force. And again, actually air resistance is not a constant value. It gets bigger as speed increases. Eventually, you reach what we call terminal velocity. And in that free body diagram, both the arrows would be the same what? Same size, same length. Okay? And the idea is the parachute makes terminal velocity less terminal, so to speak. Put your pencils down, look up. Is that okay? So I showed you the free fall video before Christmas, and that was purely in terms of acceleration. But now we're looking at it in terms of the forces that were going on, and now we're including air resistance. I hope you understand what was going on a little bit better. Yes? Okay. Courtney said 20 minutes. I'm going to skip example 5 just for you, Courtney. We already watched the video, Why the Earth Spins Part 2. So I'm just going to give you some homework in the take-home quiz, and I'll give you the rest of the class, 20 minutes as it were, to finish this. Number 1 is good. This is, again, a bathroom scale. Whenever I'm talking about a bathroom scale, Riley, which force am I really talking about? And here, I gave you the scale reading in kilograms. How would I change that into newtons? There you go. Okay? So 1 is good. 2 is good. 3 is good. 4 is good. 5 is good. 6 is good. I'm going to skip 7. I'm going to skip 8. 9 is good. 10 is good. 11 is good. I'll skip 12, 13, and 14. I have a